Dr. Rico here. This is a lecture from my mini course, Robotic Planning and Kinematics. The syllabus and notes are in the description. All right. Section 3.4, Forward and Inverse Kinematic Maps. Part of the chapter 3, Configuration Spaces. In this section, we will discuss how to transform motion planning problems from the workspace W to the configuration space Q via forward and inverse kinematic maps. Given a motion planning problem in the workspace, move from point P start in the workspace to point P goal in the workspace. We need to translate this specification into the configuration space, i.e., move from the configuration Q start in Q to the configuration goal Q goal in Q. Rather than presenting a general framework, we discuss a specific example, the two-link robot, and a specific motivation. Figure 3.15 below is the picture of a robotic manipulator commonly used in pick up and place or pick and place and assembly applications. So here we go. This is a Yamaha pick and place robot. Manipulators with this configuration are referred to as Selective Compliance Assembly Robot Arm, or SCARA in brief. From Wikipedia, by virtue of the SCARA's parallel axis joint layout, the arm is slightly compliant in the XY direction, but rigid in the Z direction, hence the term selective compliant. The joint axes here are vertical in the Z direction here and vertical in the Z direction here, which allows it to be very rigid in terms of Z direction moments bearing that load. However, if you look in X and Y, it's more compliant because it moves with the joints. So, in a vertical view, this manipulator is equivalent to the two-link robot we just studied. The end position of this manipulator is the position X, Y, where the end effector is attached. The end effector is the device with which the manipulator interacts with the environment. For example, a robot gripper for pick-up and place applications, a welding head, or a spray painting gun for graffiti. In short, we next consider the two following problems. The forward kinematics problem, which is to compute X, Y as a function of theta 1, theta 2, which is to say, compute where in the workspace you are given some place in the configuration space. And the inverse kinematics problem, compute theta 1, theta 2 as a function of X, Y, which is to say, compute the configuration as a function of the workspace position. Note, in the forward kinematics problem, we are given the joint angles, and our goal is to find the position of the end effector. In contrast, in the inverse kinematics problem, we are given a desired end effector position, and our goal is to find joint angles that place the end effector at the desired position. Forward and inverse kinematics for the two-link robot. Consider the two-link robot with configuration variables theta 1, theta 2, and end effector location XY, as in figure 3.16, shown down here. Because the two joint angles, theta 1, theta 2, are the configuration variables, it should be possible to express XY as a function of theta 1, theta 2. Some basic trigonometry leads to equation 3.1, which computes X in terms of theta 1 and theta 2, and Y in terms of theta 1 and theta 2. A function of the configuration variables that describes the position of a specific point of the body is usually called the forward kinematics map. So, this equation references 3.1 is the forward kinematics map for the two-link robot. Next, we are interested in computing what are possible configurations, theta 1, theta 2, when we know the end effector is at position XY. In other words, we are interested in the inverse function. We start by noting that such a problem does not admit a unique solution, as illustrated in figure 3.17. So here we see that for a specific P2 location of the end effector, we have these two different orientations. Okay, so one orientation, this is called the elbow down orientation. We can move to the end effector position, P2, with the links in this configuration. And we also have this so-called elbow up configuration where P2 is also reached, but this time from the other direction. We compute the inverse kinematic map as follows. In a triangle defined by P0, P1, P2, so P0, P1, P2, define gamma, an element of the interval 0 to pi, as the angle opposite the side P0, P2. Okay, so P0, P2 is this hypotenuse, right? See figure 317. This triangle has sides of length A, which is L1, B, which is L2, the length of the first link, the length of the second link, and then C, square root of x squared plus y squared. For this triangle, the law of cosines, which is stated as this, leads to the following equation. And in turn, we can solve for the cosine of this angle, gamma, which is given here. According to the discussion in section 3.5, the appendix at the end of this chapter, there are either 0, 1, or 2 solutions to this equality. The right-hand side is in the range -1 to +1, which is to say, it's in the range of possible values for the left-hand side, so a potential solution here, if and only if this right-hand side is in that range. And you can learn from that that the range of potential solutions occurs for the square root of x squared plus y squared in this interval, okay? So for end effector positions x, y, such that root x squared plus y squared is in the range, absolute value of L1 minus L2 to L1 plus L2, there always exists exactly one solution, gamma, in the range 0 to pi. So equation 3.2 equal to gamma, which is the arc cosine. So you just take the arc cosine, and if this solution exists, this will be the value of gamma in the range 0 to pi. Finally, it remains to compute theta 2 as a function of gamma. So going back up here, we see that gamma is this interior angle, and we have the angle of this being theta 1 and the angle of the second link being theta 2. So theta 2 remains to be computed. From the figure, it is clear that theta 2 is equal to pi minus gamma for the configuration with robot elbow down, which is the left-hand figure, the A figure, and theta 2 is equal to negative pi plus gamma for the configuration with robot elbow up. We summarize the discussion in the following proposition. Proposition 4.1, inverse kinematics for two-link robot. Consider the two-link robot with configuration variables theta 1, theta 2, and link lengths L1, L2 as in the figure. Given a desired end effector position xy such that it's in this range that is valid for solutions for us, outside this range, we can't reach it with this robot. There exist two possibly coincident solutions for the joint angle theta 2 given by the elbow down and the elbow up equations here. The two solutions correspond to the diagrams of figure 317, the left and the right hand side. We leave to the reader in exercise E3.7 the following tasks. 1, the interpretation of this condition that root x squared plus y squared is between these two values, L1 minus L2 and L1 plus L2. And 2, the computation of the other joint angle theta 1, which is the angle of the first joint. All right, that's all I've got for this lecture. I'll see you next time.